So the key thing is exam 1 is Friday. And the topics are everything up through strain and constitutive, so no principal stresses. Anybody have any questions about the test? I'm planning today to just put a problem up here and give you time to do it, and then I'll go through it, just make sure everyone's on the same page going into it. Yep.
Is the test going to be similar in style to the dynamics exam?
Yeah, I mean, it's going to be, all my tests are always like, you could basically, like, whatever question I give you, you could basically find a daily problem that's like, oh, this is the same kind of thing, you know?
It might even be dynamics problems.
It could. That would be an accident, though. But accidents do happen. I actually, like, one of my first years teaching here, I gave a college physics class, like, the thermodynamics final or something, like, and it took like 5 minutes before the first brave person was like, are you sure this is the right test? I'm like, oh my God.
Did it say like thermodynamics at the top? Or?
I don't remember any details like that, but I just remember just people just looking at it like, I am screwed.
It only said this is worth 15% of your grade.
Right.
Now, if you had given the physics exam, the thermo,
they'd be happy.
No
No one would have said anything. You're right about that. And then the weekly assignment, like Dan said, this is stuff that this is stuff that's relevant for the exam. So if you want to work on that as part of your studying, you know, it's good. Right now, it says in the announcements, like, the weekly assignment is attached below and nothing's attached. But if you go to content, weekly assignments, it's there. And I'll get that put up in the announcements too. Okay, so here's the question. So we have this rectangular solid material sample. This distance is 3 centimeters before the deformation. The thickness is 0.005 meters. And the height is 0.1 meters. And after the deformation, so I'm going to use a coordinate system like this. My y is going to go back this way. My x is going to go, I guess I'll go up. And my z is to the, yes. Okay, so X is the long axis like you're used to. It's not like that one problem where you had to do it all in a funny orientation. And the y-axis is this one that starts out as 3 centimeters. And after the deformation, so this deformation is caused by putting it in tension of 1500 newtons. And it leads to a deformed X length of 0.100008 and a deformed length in the Y direction of 0.029999, and that's it. These are in meters. Okay, so start out by, so the first part of this problem is calculate the Young's modulus and the Poisson's ratio. Start thinking through this together. So first of all, you can calculate the XX stress as 1500 divided by the cross-sectional area. And the cross-sectional area is, this is an area that's perpendicular to that force. So the area that matters here is going to be 0.03 times 0.005. And if you do that, I think you get 1 times 10 to the 7th. Is that right?
Yep.
The XX normal strain is 0.1408 minus 0.1 divided by 0.1. And for that, we have 0.8 times 10 to the minus 4th. And so the Young's modulus is sigma XX over strain XX. That's 1 times 10 to the 7 divided by 0.8 times 10 to the minus 4. And you get a value of, it's like a nice round number.
Yeah.
125 times 10 to the 9, is that what you got for Young's modulus?
Yeah. 1.25 times 10 to the 11.
That's another way to say it, yeah. I choose to say things in the way always that would make the math professors the most angry. So,
When he says that, you the professor.
yeah.
Is that gigapascals?
Yeah,
So that's convenient.
right,
Yeah.
yes. And then for Poisson's ratio, we're also going to need to know EYY. So EYY is LY minus starting divided by starting. So that is 0.0249 minus 0.03 divided by 0.03. And you get negative 2.56 times 10 to the minus 5, I think.
I got 30.3 repeating. Negative 30.3.
Okay. 0.0299. Yeah, I got that too.
3.33.
Yep. Negative 3.33. And so now Poisson's ratio is negative of the negative 3.33 times 10 to the minus 5 divided by 0.8 times 10 to the minus 4, otherwise known as 8 times 10 to the minus 5. And so for this, I get 0.416.
If you round up, it's 7.
If you what?
Round up.
To what?
0.417.
Oh, okay. Okay. Oh, you got 3 repeating.
Yeah.
Okay. I'm going to leave it like
I used the unrounded value.
Okay.
That's a repeating part. That's probably why. But I don't think.
Okay, so now that we have Young's modulus and Poisson's ratio, we can calculate that full compliance matrix. So now for part B, like really what you want is the compliance matrix and the stiffness matrix, but let's take a little little detour. So I didn't give you a measure of the deformed length in the z direction, but calculate what that would be. So what would LZ have measured? In a tensile test, the strains in those two off-axis directions are going to be the same. You can see that from the Poisson's ratio equation because like that last thing that I wrote on the board, everyone but you two can see this because there's a screen in the way. But the Poisson's ratio is negative EYY over EXX. It's also negative EZZ over EXX. And so if it's the same value, EYY and EZZ have to be the same. So we know that EZZ is going to be LZ minus its starting length divided by its starting length. And it has to be equal to negative 3.3 repeating times 10 to the 5th.
Which one? Yeah, it should be to the negative.
Yeah. And so I think what you get here is LZ should be equal to like 0.005 and then 3 zeros and then 1 6 repeating. Is that what you got?
Shouldn't it become smaller?
It should be smaller, you're right.
I got 0.00499.
Yeah, because I didn't, yep. Okay. Negative 3. So this should be 0.004, and then 3 9s, and then 8, and then 3s repeating. That looks better, right? Okay, so now, let's say that now that we've done this tensile test, we know that there's a strain, a Voigt strain of -1 times 10 to the -5, +5 times 10 to the -6, 4 times 10 to the -6, 8 times 10 to the -6, 2 times 10 to the -5, and -1 times 10 to the -6. What's the stress at this point? The Voigt stress at this point. For this, the program that hopefully you have is a compliance matrix program. So you'll go like, you'll run something like this in your calculator with 125 times 10 to the 9, and then 0.417. And that'll give you this matrix with tiny values, and then take that answer to the -1, and that'll give you 6 by 6 with huge values. This one is the compliance matrix. This one is the stiffness matrix. And now your Voigt stress is going to be that stiffness matrix times the Voigt strain. And what I got was -1.1 times 10 to the 6, +2.2 times 10 to the 5, 1.3 times 10 to the 5, 3.5 times 10 to the 5, 8.8 times 10 to the 5, and -4.4 times 10 to the 4. And that's in pascals. Is that what you guys got? Okay. Any questions about that? So if I had given you a stress tensor, say, or a stress cube, you could put it in the Voigt form, multiply by the compliance, and that would give you the strain. But if I give you the strain, you got to do the stiffness matrix, do the inverse, so you can calculate the stress. So now, part D, calculate the Voigt strain in a coordinate system that's rotated +30 degrees about the y-axis.